Good afternoon. I'm going to do a new slideshow. This is a dry run. It's my first attempt, and I'm soliciting feedback. So if you find it too difficult or obscure, send me a note. Let me know. Maybe I can improve things here. Now, there's my oral presentation now, which is somewhat off the cuff. I'm going to discuss this more as I would a teacher group where we're sort of developing this together. So my patter, my narration, is not necessarily the one you would want to use when you're presenting these slides. So picture yourself presenting these slides and ask yourself, would you be able to? What's the barrier between you and presenting these slides? Now, I'm going to call it a particle zoo, and people are going to think, well, that means you want to talk about physics, but I just want to allude to physics, which has a particle zoo, right? There's all these like what's-ons, right? Electrons, fermions, bosons, all these different things. It's a zoo, and this is kind of like that, but here we're just doing like pure geometry. But there is the transformation of one particle into another concept here anyway, so there's some similarities like how the A transforms into a B or how a E transforms into a T. And there are basically 5 modules that are at the core of Synergetics 2. This slide, though, is also showing critical path, and if you dive into that and to Grunch of Giants and other stuff, I think you will have to conclude that Fuller is kind of a cold warrior, historically looking back. He's all caught up in sort of the military response to not just World War One and Two, right? He's promoted up through the Navy, and he meets a lot of people that way. And through the rest of his life, like Critical Path is full of all this sort of sounds kind of like national security information, right? There's the aircraft carrying submarines, there's the kind of Intel Q, Google Earth kind of translating keyhole into civilian products kind of theme. That's all in Critical Path. So if you just read Synergetics, you might miss that about Bucky, right? So I'm trying to give a more complete picture of the guy and his place in history and come at it from a slightly different angle. And this would be like what a DEW line, the Defense Early Warning System domes, what they would look like more like today, right? This is not just made yesterday or anything, but it's kind of what a modern weather station looks like. And you can see it's almost a complete sphere, which is Fuller's original sort of thinking about these things. They're not always like fractions of a sphere. And it has an interesting pattern on it. You see the pentagon standing out clearly. You assume there are other pentagons, but there's a great variety. The book by Edward Popko, who passed away not too long ago, gets into it. It's called Divided Spheres and different ways to build these kinds of things. So then I want to introduce immediately the importance of tetravolumes to the Bucky math or synergetics philosophy, whatever you want to call it. The fact that his unit of volume compared to our unit of volume or an XYZ unit of volume is a tetrahedron number 1, and if you want to relate them, probably the easiest way is a cube of edges r being the radius of some unit sphere. Pick a sphere, any sphere. That's going to be your standard, and it's going to have a radius, and it's going to have a diameter. That ball, I'm going to show you that ball way at the end on the last slide. So you're holding a ball, any ball, tennis ball. Its radius is a certain length, right? Say 3 inches. You make a cube out of that and call that your unit of volume. That'll be on the right side. And then on the left, I've got this tetrahedron of edges D. That just means twice the length of the cube of edges R. And believe it or not, that tetrahedron of edges D, and I don't say this drawing is precisely measured or anything, but it's slightly smaller. Even though the edges are twice the length because of how sharp and everything, a tetrahedron is, it's not quite this, it's a little bit less than the volume of the cube, but they're still pretty close. So we go back and forth. We have what's called a conversion constant there. And we have algebraic ways for computing a tetrahedron's volume. Because if we're not just going to do it the usual way, and if our cube isn't going to have a unit of volume, if it has whole number edges like 1, it's not going to be a unit of volume. The cube now is kind of going to go out of focus. It's still going to be there, though, as volume 3, because the tetrahedron divides into a cube 3 times. So if we have a cube, let's keep it at volume 3 with the tetrahedron inscribed as face diagonals. So we can talk, it's up to you as the presenter, how deeply, how far into quadrats you want to go, quadrate coordinates. I think it's reassuring to some people that there's some substance here, there's some content. We can use an alternative coordinate system. We can derive the volume of our tetrahedron. We can express it algorithmically. We can derive it through computation, of course, and put that on a computer and have lightning fast computations, right? Even though that looks more involved, that determinant and stuff's kind of scary looking. But these are the volumes that you get, so the payoff is worth it. You get these whole number volumes for these very clearly interrelated polyhedron. Now this doesn't show exactly how they're interrelated. The orange tetrahedron would be the face diagonals of that volume 3 cube, as we were discussing. Edges are the same for the volume 4 octahedron, and for the dodecahedron on the right, the blue one, it's the long diagonals of its 12 diamond faces that are the same as the edges of the tetrahedron. But those are nice whole number volumes that we currently don't purvey. Those are not part of schooling today because this whole idea of a tetrahedron as unit of volume is novel. It's something that you find in Synergetics, and people haven't really decided it's worth exploring further unless you're part of the subculture that's been chugging along now for the last half century, and we have developed. We do teach classes. There are kids coming through our classes. This was at Reed College some years ago, but the students were young. This was like a summer school, and they all made these A modules. So I'm showing you what the A modules are. We're going to go through B-E-A-S-T, but we're starting with A. 24 of them make this regular tetrahedron. We're just partitioning space. Like, how would you divide up a tetrahedron? I bet if you thought about it and you had your bread knife, you had your tetrahedron made out of dough, you'd probably come up with probably the same solution. A lot of people would. In other words, the A module has got to be out there in the literature somewhere, but whether it's called A or not, I don't know. So Fuller starts in a very logical place. He's taking the simplest Platonic polyhedron that there is, with the fewest number of edges and faces and points, and dissecting it into left and right-handed subtetrahedra. Calls those the A modules. You get the plane nets. There's a lot you could say about them. You can give their coordinates and quadrate coordinates. And then we go back in history and see how Robert Williams here was very eager to get a first look at synergetics. There was a lot of buzz in those days. And in 1960, a preprint was placed in some library repository, and Robert Williams goes and checks it out, and he's starting to get that there's A and B particles in synergetics, and he develops A and B particles too, based on that, except he's changed the name a little bit. Now, he wouldn't think that would be too significant, but of course it is to change the nomenclature. He at least gives a footnote and describes what Fuller is calling the B module. So you've seen the A module. The B module you get pretty much the same way. You kind of dig into each face of the octahedron and carve it up like you'd carve a pumpkin or something. You carve it in such a way that the A modules are all already there. In other words, this tetrahedron, this eighth of an octahedron, is in a sense deeper. It's got different angles, so there's a difference between the A module and the B module, and the two added together give basically a section of an eighth of an octahedron. We've got the plane nets, and once you see how the B is based on the A, you can extrapolate to a C, a D, and E, all of the same volume. We talk about that. So just remember these two as a pair, the A and the B, and then you see how there's another view of that. You see how that can start a mite. You put two A's together, a left and a right, and then you put a B on either side, either a plus up, a left or a right, plus or minus. And this gives you a space-filling tetrahedron. You can't tell, unless you're looking at the dissection, if it's a left or right-handed mite. It's like that goes away. Mites don't have handedness, even though there's these two ways to build them. And they're also space fillers. And this gets us into the whole discussion of what tetrahedra fill space without handedness. There's no chirality here anymore. These are not enantiomorphic tetrahedron. The mites are all the same. And we find in the literature, if you look into Goldberg, Somerville, other mathematicians who, there aren't that many, who study which space-filling tetrahedrons exist, they come up with the same ones Fuller does, except Fuller, what he calls the right, he doesn't get that the quarter right and the half right are also space fillers. He doesn't get to that. In fact, quite a few of the results that we're showing here, he didn't get to. One of which was just to restore phi, some people say phi, back into synergetics. It's like it's second root of 5 plus 1 all over 2. That's what this number is. But it shows up everywhere when especially five-fold symmetric pentagonal kind of geometry. That ratio is always there. And so once we fade that back in, we have simpler ways to express other volumes in tetravolumes, as shown here in this chart. You've got the 1, 3, 4, 6 that we looked at earlier, but now also the five-fold symmetric pentagonal dodecahedron and icosahedron, both Platonics. The icosahedron's edges here are the same as those of, say, the octahedron and tetrahedron. The pentagonal dodecahedron is sized such that its edges would cross those of the icosahedron right in the middle. And those two duals of each other, crisscross, make another polyhedron called the rhombic tricontahedron. And that appears in our story several places at different sizes. The super RT, the biggest one we often talk about, is just what I described. The icosahedron and pentagonal dodecahedron, both shown on this chart, crisscrossed, give the RT. So that's a whole discussion. What is a dual? And then talk about how the duals can sort of crisscross to give birth to additional polyhedron. Here is the rhombic tricontahedron. And if you think about it, the long diagonals of these diamonds, like you can see a big triangle facing you, that would be one face of a 20-sided icosahedron, 20-faced, 20 eyes, 20 openings, right? And so the short diagonals likewise form the pentagonal dodecahedron. So when you crisscross these two Platonic these two Platonic polyhedra, you get this one, the rhombic tricontahedron, which you can then crisscross its faces and sort of drill into it, much as you did earlier with triangular faces, but now they're rhombic faces. Instead of drilling into a tetrahedron or an octahedron, we drill into this rhombic tricontahedron, and we get 4 modules per face, 30 faces, 120 modules, 60 left, 60 right. They're inside out of each other. Like you can fold them one way or another and you get left or right. And these define what we call the T and the E modules. And they're the same shape as one another, so it's just a matter of scale. And the difference between the two is very small, relatively tiny. Like once you build one, you'll find that the next one is like, you'll have to make it pretty big to see the difference, let's put it that way. 120 E modules, we call them, make a rhombic tricontohedron that exactly circumscribes a sphere. As Bonnie says in her talk, a lot about what's going on in synergetics is spheres circumscribing and inscribing vis-a-vis polyhedra, something that we do anyway in geometry, we always have. It's kind of like primordial to do that. The stuff with spheres and straight-edged polyhedrons, we do this inscribing and circumscribing a lot. So there are the two rhombic tricontohedron that we focus on in synergetics, the one where the volume is just over 5 tetravolumes, but the diameter from one diamond center of a face to the opposite center of a diamond face, that's D, the diameter of a ball. So you put our unit ball, our tennis ball, inside of a rhombic tricontohedron such that opposite diamond centers are all tangent to it, and it turns out the volume of that rhombic tricontohedron is just a tiny bit more than 5. So what do you have to do to shrink it? By what scale factor do you shrink all the edges of that RT to get another RT of volume precisely 5, not a little more? And we figure out that math. And it's a story we can go into in a slideshow like this, meant to be somewhat brief. We don't do the derivation, but we do see that the numbers correspond to what's in synergetics. Because Fuller talks about this difference quite a bit. It's important to him. So we've covered A, B, T, and E. The E is the bigger of the 120. If the ball is exactly volume 5, then we're talking about T modules. If the radius is exactly 1, then we're talking about E modules of the rhombic tricontohedron. Lastly, we talk about the S module. So even though it's beast, we're doing it in a different order. A and B are like a pair, T and E are a pair, and now the S module. So there's your rhombic dodecahedron on the left. It has a volume of 6 for us, where the long face diagonals are the same as the cube face diagonals, are the same as the tetrahedron edges, octahedron edges. And so there's an octahedron inscribed in this thing. The dotted lines actually define an octahedron, and if you cut that in a 5-to-1 ratio as shown on the right, you can define an icosahedron faces flush with an octahedron. So icosahedron on the inside faces flush with the 8 faces of the octahedron. The edges are still 2 radii. The volume of this octahedron on the right is 4. The volume of the icosahedron inside is about 2.92. It goes on, it's like 2.91, blah, 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 dot, 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 right? And there in darker blue, these posters by Casey House, really well executed, is one of the S modules, a left or a right, as you prefer. And those, there's an S module there. Those you can phi scale in our system. And this we owe to David Koski and his research. And when you phi scale the S module and the E module, you end up with a new way of expressing ordinary conventional concentric hierarchy volumes like 1, 2, 4, so forth. Whatever shapes we have. We don't actually define a 2. That could be 2 face bonded tetrahedron or something like that. Anyway, this skew icosahedron, that can be developed from a cube octahedron inscribed in an octahedron. Cube octahedron, you can kind of see it there. It's got alternate square faces, and if you sort of twist its triangular faces without letting them lose touch with their octahedron faces, they stay flush the whole time you twist, you get an icosahedron. And it turns out that something we call the S factor can transform the cube octahedron of 2.5 into that icosahedron of 2.92 or so, just by multiplying the volume of the 2.5 by the S factor, getting an an output, and multiplying that output again by the S factor. What is the S factor? Have I described the S factor? The S factor is the ratio in volume of the S module and the E module. And you'll remember the E module is 1/120th of a rhombic tricontahedron, whose volume is a little more than 5, but which shrink wraps what we call an IVM ball, a unit radius sphere. So going forward, we do this phi scaling thing where we have a nice notation for the S module that we scale it up and down. Like if you multiply all the edges of an S module by 1.618, ... it obviously gets bigger. All the edges don't quite double in size. They go 1.618 in size, so the volume goes up as a third power of that. You're keeping the shape. You're taking this sliver, this wedge. You can 3D print an S module. It's a partition, a particle. It divides an inside from an outside, like all these modules. And then you can scale up all the edges by phi, and the volume will go up by a factor of phi to the third power. And then you can scale it up again, and you get S6, S9. So we go up 3 powers of phi every time because the volume goes up as a third power of the linear scale factor, which is each time phi, right? We play the same game with the E module. Notice we can also go down. In other words, we can take an E module and scale it down by 1/phi, 0.618, and the whole thing shrinks by 1/phi to the third power, volume-wise. So volume goes down in chunks of 3. So we have that notation now. S6 means we've gone phi up twice on an S module. We've applied phi, it's grown. We've applied phi again, it's grown. Each time by phi to the third power. So we call that S6. It's like think of beer mugs. S6 is a much bigger S module, like a bigger beer mug. Same shape, just bigger. And S3, again, is just one step bigger. But those two, S6 plus S3, they add up to 1. So we get the volume of a tetrahedron. And so on for the volumes of these other shapes we've been discussing. The rhombic tricontahedron made out of T modules. That means that it has a volume of exactly 5, made out of E modules, and so forth. And there's the super RT we were discussing. It's equivalent to 480 E modules and 120 E modules down a step, 1/phi times the edges. So we call these the Koski identities. And it's very interesting that these whole number volumes over on the right plus irrational volumes can all be expressed as sort of linear combinations, as we say, of phi scale S and or E modules. And here we see the actual computational results using arbitrary precision. I think this was 50 digits. And when they don't resolve to a simple whole number, then in column 3 you get the algebraic or symbolic expression for these different volumes, again in tetravolume, and that's roughly the concentric hierarchy as a picture above. The cyan color, say, was the icosahedron. The cyan is the icosahedron with the same edge lengths as the yellow cube octahedron. Then we have the blue rhombic dodecahedron of volume 6, the red octahedron of volume 4. So in the chart below, what you're looking at are the volumes of shapes depicted above. And here again is that progression, the concentric hierarchy. And the IVM ball I'm talking about is this brown ball that just appears in one of the frames. And then we're wrapping around it, basically. We've got our rhombic tricontahedron of E modules, for example, is the purple shape, just wraps it exactly. Building outwards, we've got tetrahedra of volume 1, cube of volume 3, octahedron 4, rhombic dodecahedron of volume 6, and so forth. out to the yellow cube octahedron of volume 20. Volume 20 times 1 over the S factor will shrink it down volume-wise to that icosahedron, meaning the ratio of this cube octahedron to the icosahedron as related by the jitterbug is equivalent to the ratio of the S module to the E module, which we find interesting and all part of tying it all together. What does it all mean? Does it mean something in terms of particle physics or energy, or can we use this as physics? Let's say I'm not going to even address that question right now. It's a tautology at this point. It's just a geometry that works really well and it's easy to carry around in your head. You can relate these polyhedra reliably and compute with them reliably using this system. So why not tackle it? It won't crowd out anything else. In other words, you already have other ways of thinking about these things. Keep those other ways and add this as an option. I think you'll find it was worth your time to do that, and you'll get a better appreciation for history as well, because Fuller was an active player throughout the 1900s, and his influence is strong to this day. All right, let me know what you think of that. I'm maybe going to be adding some slides, tweaking them based on comments, feedback. I'm happy to change the narration. And for those who know my style, even if I don't change the slides at all, chances are I'll come through here in a few weeks or days and do it a different way with a different pattern. Because I don't believe in there's just one way to always do these slides, right? And that's where you come in. If you do them too, do it your way. All right, talk to you soon.